filtered. It's actually an EPA requirement that surface waters be filtered, and that's a logical requirement. So here we have this technology that's been in use for a very long time, more than 100 years, and we're trying to figure out how it works. And so I want to take you down that path of exploring what might be going on inside filters. And then, as we have been doing, sometime shortly after 3, we'll break and we will go to gather, and you can start working on the next assignment. And maybe right shortly after 3, I'll switch and just give a few pointers about that assignment. Okay, so we're going to talk about filtration model, which is about removing little particles using big particles, where the big particles are the sand grains, and somehow we're using sand grains to remove things as small as bacteria. Just a note about that: slow sand filters were the first. The first sand filters were, of course, called sand filters, right? They were filters made from sand. They were called sand filters. And later on, we eventually started calling those first ones slow sand filters. And when those first sand filters were built, they didn't even have germ theory yet, because germ theory came along in the late 1800s. And the first slow sand filters were built around 1829. So that means that they built the filter to improve water quality, not knowing that they were trying to capture bacteria and other pathogens, and not having any idea how that filter was actually working. And yet, like, this is just one of these amazing maybe coincidences or just stroke of good luck, that it turned out that the filters made out of sand actually did remove bacteria. And that is the big puzzle. Like, how does a sand grain that's several hundred micrometers, so 0.2 perhaps millimeters in diameter, several hundred micrometers in diameter, remove an organism that is just 1 micrometer in diameter? So that's what we're going to puzzle out today. So these are some mysteries about filters. Filter pores are gigantic compared with the particles that they remove. There's something happening, we call it ripening, which gives a sense that there's something biological happening in these filters, like it's a fruit that tastes better after it's gotten riper. The filter somehow ripens and works better after working for a little bit. Although an insight that comes from that is that clean sand is somehow a lousy filter. And I'm just wondering if you're going to start maybe pulling things together from what you've learned already in this class. If sand is actually a lousy filter, what's the actual filter? What is actually filtering inside the sand? Another mystery: filters don't fail by clogging, they fail because particles start leaking through. So it's not because you can't push the water through anymore that they fail. They fail because particles start leaking through. So particles start coming out the bottom of the filter. And so I'm beginning to lead the witness. I'm beginning to lead you now. Flock filters have limited capacity too. Remember this from flock filtration, that the flocks in the flock filter, they can only take up so many small particles, and then they become less porous and they become useless because there's no more water flowing through that flock filter. So this is the similar kind of thing is happening in sand filters. And then another insight is that our mystery is that when the filter fails, as in particles start coming out the bottom of the filter, only a tiny fraction of the pore volume is actually filled with captured flocks and particles. So it's not because the pores get full that it fails. Something else is going on. And there's the question: what is happening inside those pores? So I want to share some results from some experiments that some students did a few years ago at Cornell. And this is just an overview of their apparatus. So they've got some water coming in. They're making the water dirty themselves. So they're adding clay to the water to make it dirty, a clay suspension, not a solution. And that water is going through a turbidity meter so they can see how dirty the water is. And then they're adding PAC, which is the polyaluminum chloride, or the coagulant. That's being pumped in. It's going through a flocculator, and then it's going into the filter, and it's going into another turbidity meter so they can measure how clean the water is coming out. So they ran a bunch of tests, and this is some of their data. And we're seeing time on the x-axis in hours, and we're seeing effluent turbidity, so the filtered water turbidity. And you should know that they were filtering 5 NTU water. So the water going in was 5 turbidity units. And coming out, it's, I can't see exactly because it's way down at the bottom here, but it's something like 0.1 or 0.2 NTU. So the water leaving this filter would have met the EPA standards, which is 0.3 NTU. They noticed there was no clarifier in this schematic. So there's a flocculator, and then it goes right into the filter. That's called direct filtration. You can do this if the water is pretty clean so that the filter can actually handle all those solids. And in this case, that means that we know exactly how many particles are going into the filter because we added 5 NTU and all of them are going into the filter. Okay, and then they varied the coagulant dose. And so we get to see what happens as you vary the coagulant dose. And let's start with the very lowest coagulant dose that's on here, which is 0.2 milligrams per liter. That's these orange dots. And you see that it didn't perform real well as far as the turbidity was a little bit higher than the other ones, but it kept on working for a very long time. So that's interesting. And they didn't actually take that one to failure, like it was still working when they quit. And then we'll increase the coagulant dose a little bit more, go up to 0.65. Now we're the yellow dots, and look at this. Now it starts failing around 6 hours. You see that? The turbidity starts rising up, maybe a little bit before 6 hours, and it just goes up. And then we'll go to another extreme, we'll go all the way back to a very high coagulant dose, 1.55 milligrams per liter. And that one fails after 2 hours, and it fails very fast. That line is very steep. Turbidity comes up very, very quickly. So these are results from real filters. And the question is, well, what's going on inside the filter? And it's very similar to understanding what's happening in the flock filter, in that we've tried, but we can't really have cameras that show us exactly what's happening inside the filter in real time. And so we're left with watching what happens going in and going out, and then trying to figure out, well, what must be happening inside this black box of this filter? So here's my story of what I think is happening. So there's this idea that somehow the filter is slowly getting full, and in the end, particles come out the bottom. And that's the first insight, that particles are getting pushed deeper and deeper into the filter over time. And so maybe it would make sense that the particles are initially being caught near the top of the filter. And then as it continues on, the particles are getting pushed deeper and deeper into the filter until finally at failure, they come out the bottom. And so this is an animation that kind of proposes that. So that there's a filter off to the right on the screen. And I've got 2 graphs here showing head loss. So the pressure drop across the filter, head loss across the filter, and turbidity coming out of the filter as a function of time. And this is what happens. So head loss methodically just goes up linearly over time. Turbidity gets better and better. And look at the brown going down through the filter. That's like showing the filter getting full. And at the end, particles start leaking out the bottom of the filter. And we see that in the turbidity going up quickly as the filter becomes full. Do you want to see that again, or did it make sense? We're good. Okay, thumbs up.
Professor?
Yes.
I have a quick question about the graph on the previous page. So the system that they had, that one did not have a sedimentation tank, correct?
Correct.
How would those values change if a sedimentation tank was inputted into the system?
Great. So a well-performing clarifier would have turbidity coming out that would be under 1, less than 1 NTU. And so all things being equal, that means that the loading of particles into the filter would have been reduced by a factor of 5. And that would suggest that the time it would take for the filter to fill up, whatever that means, would be 5 times as long. And so maybe instead of failing in 6 hours, it would fail in 30 hours. Yeah.
Perfect, thank you.
Okay, so we did this. So this is really powerful, like this insight that, oh, particles are loading from the top of the filter and then they're slowly filling in lower and lower. That's a really cool insight. And here's what we see in the course of time. There's this initial period when performance is bad. It's a combination of backwash, debris that was left from the previous time the filter was clean that might be coming out initially. And there's something about the filter loading and having something about it that's making performance better than if it were just clean sand. And it's something about the particles that are coming into the filter are actually improving the subsequent performance of that filter. The turbidity coming out slowly decreases over time. Do you see that? This black line slowly drops. It's not a huge drop, but it slowly gets better. And this is commonly seen in filters, and it suggests that the removal in the brown zone where the filter is supposedly like full, that particle removal there is actually better than in the clean zone that's at the bottom of the filter. Because think about it, at the beginning of a filter run, most of the filter is clean and a little bit of it is dirty. And that doesn't perform as well as a filter that is mostly dirty and has a little bit clean at the bottom. That means that the dirty part of the filter is actually doing a better job of filtration than the clean part of the filter. So that's comparing the loaded zone and the clean zone. And in the middle, there's this active filtration zone where it's actually very effective, where particles where most of the particles are being captured. And then the filter goes through what we call breakthrough. Breakthrough is when the turbidity or some of the particles start showing up in the effluent, coming out the bottom of the filter. And I'm postulating here, you should know this, I'm talking about filtration models in this lecture today. And these are models, these are hypotheses, these are things that we're just barely understanding, that we're still hoping to learn more about. Here's a hypothesis that maybe the large flocks get to the bottom of the filter first because they have a hard time, because they're being pushed the hardest by the water, because they take up more space, there's more drag on them, and the water is pushing them the hardest. So let's look at what's happening inside the filter at the level of the pores, So what I've drawn here is 3 sand grains, which for some reason turned out to be green. Don't ask me why they turned out to be green. And these 3 sand grains form a pore. The pore is this narrow constriction in between the 3 sand grains. And that constriction, that pore, slowly fills up, but not completely, with particles and flocks that are coming in from the clarifier. And that constriction in the middle keeps on getting smaller and smaller until when a flock tries to enter that constriction, the force of drag on that flock is larger than the coagulant nanoparticle chemical bonds can withstand. And so even though the flock attempts to attach to the side of that constriction, it can't because it's being pushed too hard by the water. And so it keeps on going through. Do you see how this is such an important piece of understanding what's going on inside filters? The filters allow even the biggest flocks to just go right through the filter at the end. When the filter is full, when all these constrictions are made, flocks just go right through because the viscosity is dragging those particles right through the filter. So now you know why even a full filter can easily transport flocks from the influent to the effluent and have them pop right out the bottom. They just go sliding right through all those pores because the force of drag is greater than the bond strength that those coagulants, that those flocks might have trying to attach to the wall of the constriction. Here's another interesting insight. The head loss in the filter, this is the pressure drop or the change in water level between the water going into the filter and where it comes out of the filter, is close to linear before breakthrough. So remember, breakthrough is when flocks start coming out the bottom. So here's the first one for 1.5 milligrams per liter. That green dot marks when breakthrough began happening. And you can see that although your eye tells you that the green curve is clearly a curve and that it bends over, if you look at the place where it is not yet having broken through, when breakthrough hasn't yet happened, that part of the curve is actually a straight line. Like you're hard pressed to see any curvature in that part of the line. Here's another one. They're same thing. Like there's really no evidence of curvature in the first part of that yellow line until after breakthrough happens, and then we begin to see curvature. So I don't know if this strikes you as odd, but here we have this complicated system where we have sand getting somehow filled up with some flocks, and yet the pressure drop through that sand column just increases nicely, linearly with time. Does that seem surprising to you? Like, think about how complicated this is. Like in the previous slide, I showed you this, constrictions getting smaller and smaller. That process of constrictions getting smaller and smaller has a very nonlinear effect on head loss, right? As this constriction is getting smaller, head loss is like super rapidly ramping up because the velocity going through that pore, that hole, is increasing fast, and the head loss goes with the square of the velocity. So that is a very nonlinear process. And yet here we get this linear head loss with time. So anyone hazard a guess what makes the head loss or the pressure drop through the filter increase linearly with time? Anyone? Or tell me, does this seem surprising to you? Like, Like if I had, maybe I should have done this first. Like if I had asked you to predict what head loss will look like in a filter that is filling up with particles, what would you have guessed would happen? Yeah, like I would have guessed that it would increase slowly at first and then it would ramp up and go up really fast. Yeah. But that's not what happens. It's linear. It's beautiful when it's linear, and it means this is data that is begging us to figure it out, right? There's something happening here that's interesting. So here's what I think is happening. So head loss is directly related to what fraction of the filter is already full, meaning that the pore constrictions in that part of the filter are already as small as they're going to get. So remember, here's the idea. Each pore is slowly loading with particles and gets as small as it can possibly get until the velocity inside that pore is so fast that no more particles can attach. At that point, all the particles that come up to that pore just blow right through and keep on going deeper into the filter. So that means that the number of pores that you have to go through to get to a pore that's open and ready for more particles to be deposited is a function of how much dirt has been, or flocks have been deposited in the filter thus far. So maybe it takes, let's say it takes a minute for one of those pores to fill up. Then in 2 minutes, 2 of those pores are filled up. And in 3 minutes, 3 of those pores are filled up. And as you're coming down through the filter, by the time you get to 5 minutes, you've got to go through 5 of those clogged pores, and you've got the head loss of 5 of those pores to deal with. Did that make sense? So head loss increases linearly with time because the number of formed and fully constricted pores is increasing linearly with time. Then at the end, after breakthrough has happened, head loss continues to increase. It continues to increase some more, but it increases more slowly. And I'm at more of a loss as to what's happening here. Maybe the pores are continuing to constrict a little bit more. Maybe some small particles are able to deposit on the inside of a pore. Maybe a big particle can't constrict because it just gets pushed through by the force of the water. But maybe a small particle can attach to the side because it's experiencing less shear. So maybe the pores do continue to constrict a little bit, or the flocks that make the constrictions are becoming less porous. So now I'm reconnecting this to what we think we understand about what's happening inside flock filters. Remember, in flock filters, some of the water is flowing right through the flock. And the flock is slowly becoming less porous because particles are being captured inside that flock. So maybe the same thing is happening here. Do I have a video of this? No, I have an animation at some point soon about this. Here's another insight from these graphs. Breakthrough happens sooner with higher coagulant dose. So why does the increased coagulant dose result in earlier failure? Why does more coagulant make it not last as long? So here's the hypothesis. If you add more coagulant, then there was a flocculator before this filter. And that flocculator was a relatively small G theta, relatively little deformation of the fluid. As we increase the coagulant dose, we increase what fraction of the clay particles are coated with coagulant and how much sticky surface there is on each clay particle. That means that when two clay particles attach, if the coagulant dose is higher, the probability that those two particles attach is higher, right? If you increase the coagulant dose, then the chances that you hit sticky when you come together is greater. And so the flocks inside in the flocculator are going to grow faster and larger when we add more coagulant. So it's possible, because we didn't have any clarifier in this system, that we produced bigger flocks when we added the coagulant, more coagulant, and those bigger flocks occupy more volume. And this is because they're fractals. Remember, flocks are fractals. So if the amount of water that's part of the flock increases as it increases in size, and so these bigger flocks effectively occupy more volume. Why is the head loss accumulation faster? Well, we have more coagulant. I'm actually less sure on that one. This still needs some more model development to figure that one out. Now, I showed you the very first slide was the image that's up on the right top corner, which is actually 4 glass beads from the top of a slow sand filter. And in the pore that's formed by those glass beads, so this is a glass bead, there's a glass bead here, there's a glass bead here, and there's one here. And then in this pore, there's this stuff that's being deposited. Now, this was a slow sand filter that didn't even have a coagulant. But what's fascinating is, like, I don't know where you would have imagined particles would be removed inside the pores that are formed by sand grains. But I would not have predicted that they would be captured at the narrowest space in the pore. But that's what appears to happen. We can see it in that photomicrograph from those sand grains. And I bet that we can think about why this must be happening. So we'll do this by looking at what happens if we take a straight tube and we run some particles through it. So here they go. And those particles that went through that tube, there was nothing that was transporting them to the surface of the tube. So if they got into the tube, they just went right through it. There was nothing that made them get closer to the tube wall and hence have an opportunity to attach. Let's take those same particles and run them through this hourglass shape. So now, when they go through that constriction, because the streamlines contract, they actually get closer to the wall. Does that make sense? If you're flowing through a constriction, you actually get closer to the wall when you go through the constriction. And if you were close enough to begin with, that little fact that the streamlines compress is enough to transport you close enough to a wall so that you hit the wall. You can only imagine this, right? You imagine you're flying down a tube and the tube gets constricted and it's still big enough for you to go through, but you end up hitting the wall at the constriction because you were going straight down through a section and the streamlines converged and you end up hitting that wall. So that's what's happening to these particles. And this is why particles are captured at the smallest places inside in the constriction of the sand. So particles are deposited at the constriction. And here's this other insight. The biggest part of the filter pore remains empty. So this is a big aha too. There's only this one little place inside the filter that's actually doing anything for us, and it's this constriction created by the sand grains. The majority of the pore created by the sand grains is big and open and wasted and never fills up. And then this last piece is the big particles can't attach to a partially filled restriction because the force of drag acting on those particles is too large. And so they just get pulled right through or pushed right through. Okay, and if we think about a filter that is operating in an agua clara water treatment plant where there's a clarifier first and then a filter, how big are the particles that are getting to the filter? So here's a plot of terminal velocity of particles as a function of what those particles are made of, the density of what they're made of. And the purple line is the capture velocity in our plate settlers. And so if we take 0.12 millimeters per second as our capture velocity, we get a flock that's about 27 micrometers. And that would be the largest flock that would tend to escape the plate settlers. Okay, so that's the biggest flock that we would expect to see getting into our filter. And of course, the clay might start out as a few micrometers in diameter. So it's a whole bunch of clay, nonetheless, inside this flock. And a hypothesis, and means I'm at the edge of knowledge here, I don't actually know, but maybe these constrictions that are made up in the filter are made up primarily by the larger flocks that are making it out of the plate settlers and into the filter. And so there are a bunch of 20 micrometer blue dots placed on top of the flow constriction that I showed earlier, showing how they could kind of make this flow constriction. And then of course, smaller flocks are going to fill in the gaps between the bigger flocks and make this continuous structure that is this constriction. So this, is it clear what I'm trying to draw here? This is this constriction that is forming, that is being made up of flocks. And this is the remaining hole through that constriction that all the flocks that don't get caught travel through. So here's a couple views of that system, and reminding you that this is going back to what I first saw in the photo micrograph that I took, goodness, back in the very early 90s, like maybe 1993. So here's this constriction. It's forming. It's tiny, but it's still large compared with a clay particle, because this is 500 micrometers up here for the size of the sand grains. And this is the size of sand grains that we use in our filters. And just emphasizing that if this red thing is flocks, that's how much of the pore gets filled with flocks. And the majority of the pore is completely empty, even though the filter is full and is beginning to shed flocks coming out the effluent. So some more thoughts about this pore. The pore that's created is an orifice, like we talked about much earlier. And that means there's going to be a minor loss associated with this pore. It might have a vena contracta, depends on what the geometry of this is, like how sharp the edges are. Because water is flowing through this orifice, it means that there's a flow expansion on the other side. There's a minor loss, and it has a minimum size because the velocity goes up as it gets smaller, and finally that causes too much drag on any additional flocks that try to attach. And then there's this other insight. Okay, that was about the pore, but now the red part of this constriction that I'm saying is made up of a whole bunch of flocks that have formed this little constriction. The red part is porous too. So this is harkening back to what we learned in the flock filter. Flocks are porous. And so some of the water going through our sand filter is actually flowing through another filter, a flock filter that has formed in the pores. And this is a weird design for a filter because some of the water effectively bypasses the filter and goes through this pore, but some of it flows through this these flocks, and inside those flocks, it has an opportunity to flow or to attach to a clay particle that is already a part of the flock. So it can attach to another particle inside the flock and be removed that way, just like the flock filters work. If that's happening, and I strongly suspect it is, then the red part, this flock filter, becomes less porous over time. And that could be the reason why head loss continues to increase slowly, even after the filter is shedding particles, because all the pores have these constrictions in them. And we've also taken a filter. My students have taken a filter, they've loaded it with particles, the experiments that I showed you, and then at the end, they didn't add any more particles, and they reduced the flow rate through the filter, and they continued to measure the head loss. And so they measured head loss as a function of flow rate. And if the filter was just porous media, just sand, you would expect that the head loss would increase linearly with flow. And that's what you would find with a clean filter. But with this filter that was loaded with all these constrictions, there was a nonlinear term. There was a v² term, which means that these flow constrictions each have a little flow expansion where there's a v² kinetic energy term that's being lost ultimately to viscosity in the next pore. So here's another question. Why is the head loss at failure lower at a higher coagulant dose? So remember we saw that result? They added more coagulant and then it failed sooner. So if we assume that most of the filter pores had formed constrictions at breakthrough, then that means that when they added more coagulant, that the head loss per constriction was lower, because the head loss was lower when the filter failed. So that means that the head loss per constriction was lower. And that's consistent with the hypothesis that larger flocks can't attach as easily because the drag force is higher, and the flocks were bigger because there was more coagulant added, and so in the flocculator they grew larger. It's also consistent with the hypothesis that large flocks are more porous, and thus more of the flow is through the red part of this constriction. It's through the deposited flock. So who knows what's going on here? Both things are possible. It's just very intriguing. Let me just breeze through this one. The insight is that the actual flock size distribution, the ratio of big flocks and small flocks that are going into the filter, are going to influence performance. And if you wanted to model what's going to happen in the filter, you would need to know what that flock size distribution is, I think. And so there's more to learn here. We don't yet have nice models that clearly describe what's going on inside these filters. Here's something about connecting how the rest of the plant works and how the filter works. If we were to improve the performance of the clarifier, then there would be fewer particles going to the filter, and the filter would have longer run times, longer times before it starts having particles breaking through. And the reason that we care about this is we're going to end up backwashing the filter. We're going to run water backwards up through the filter to clean it. And that takes a lot of water. And that water is essentially wasted or needs to be recycled back to the plant. And so we would like to reduce how much water we have to waste to clean the filter. And that means we would like the filter to operate for as long a run as possible before we need to backwash it, before we need to clean it. So that would be an argument for doing something to the clarifier to make it work even better. And of course, I would be very interested in seeing if we can figure out how to make a flock filter that works even better. You could also invest in more plate settlers. If you had more plate settler area, you'd be able to capture smaller particles, and that would improve filter runtime as well. This is a mystery. If you go to a water treatment plant and ask them, what do they have inside their filter? Most or many water treatment plants have anthracite on top of sand. And we'll talk more about how that will work maybe on Thursday. But the reason that they like the anthracite is that the anthracite is larger in size, and they find that they get less head loss development as a function of the particles that they're capturing. And so they can effectively capture more particles in that filter with lots of anthracite in it. And the question that I am struck by is, well, why do they then put sand underneath the anthracite? Because what we just learned today is that there's this active filtration layer or active filtration zone that moves down through the filter as the filter slowly is, as the voids are slowly, or the pores are slowly constricted. That suggests that the sand doesn't do anything until all the anthracite is filled up. And so why don't you just get rid of the sand and just use anthracite? I've had this question for years, and I don't know the answer to this one. And I don't know if we've had 100 years of misguided filter design because we didn't understand the physics, or if there is some other reason why having the sand on the bottom of the anthracite is helpful. I'm just posing that one as a very big question, worthy of some research. So my summary, flocks are the filters in the sand filters too. So flocks act as filters inside the sand filters. They only occupy a few % of the void volume in a loaded filter. The head loss is close to linear with time. The head loss from constrictions is due, at least in part, to flow expansions as the water exits the constriction and comes out the other side. And larger sand or larger anthracite have larger pores that can hold more particles for the same amount of head loss. So if you want to reduce the amount of head loss that you have, you can use larger pores. Larger sand grain would do that. And with that, I have a parting challenge, which maybe I guess I can pop this into the chat so you have access to this. I'd love for you to take this question to Gather and use this when you get there. So let me add this in the chat. Okay, and then I thought I would just share the screen again and show you this assignment that you're going to be working on, which is very different from what you did previously. So this assignment, instead of you creating lots of things in a part studio, creating that flocculator, this time you're going to work with pieces that we've already built and designed, and you're going to play with those designs, vary some parameters, vary some of the inputs, and see if you can understand how it's worked and see if you can actually change the design to make it cheaper. Okay, so you're going to be using the fact that there's a bill of materials there, and what I wanted to show you is, okay, this is the part studio where I've imported here a piece of our clarifier, which is the plastic pieces that are up in the clarifier. So I'm showing just 2 of the plate settlers. Here's the inlet manifold. There's only 1 diffuser being shown because I have replication turned off. So there's only 1 piece being shown of most things. And at the top here is the outlet manifold. There is a place here called design analysis where you can write all of your answers. And so that's where you can change who the authors are. It claims here the authors are Amy, Juan, and Cho, and you're going to want to change that to whoever your authors really are. And that will, so you'll be answering all the questions here, and the questions are in the textbook. And then the overrides is where the inputs are that are all the parameters that are controlling this design. And there are lots of them, okay? But what I've done is I brought the ones that you're needing to play with the most right up here to the top. And if there's anything else that you need to bring up, this is where you can make a change and it will change the design. And sure, I'll do this. It might cause things to break. I'm going to change replication to true, and I'm going to hit commit. And that will, in like a minute, give me the design showing all the plastic parts. And that will, it will still have the same price in the bill of materials because we keep track of our costs carefully, and whether or not everything is replicated, we still show the same cost. So there it is. There's my cost. You didn't see it before. There's $5,189.78. It's the cost of this system. And what do I got to do yet? I wanted to show you a cool trick for navigating and seeing inside variable maps. So there's a lot of kind of data in the form of variable maps that is available to you. You can look at it here, but you can't see much. So here you see that there's an overrides and there's a said plastic. And said plastic is all the parameters that have been calculated about this design. And I'd like to know what's inside said plastic. So here's how you get at it. You go back to custom tables, and there's another one here called variable table. So you go to variable table, and we saw in the previous one that said plastic was an option. So I type in hashtag said plastic. And now I can see all the variables that are inside said plastic. And so some of them you might recognize, like there's the width of the clarifier bay. And down here somewhere there's an inlet manifold. And at some point you're going to want to see more details of the inlet manifold. And it's also a map. Okay, there's lots of stuff inside that map. I can like drill deeper into that map by just typing, just like you kind of would expect, dot inlet, whoops, what just happened? Manifold. And now I can see inside that map. So I'm one layer deeper. And inside manifold, inlet manifold, there's yet another manifold. So I can type that manifold at the end of that. And I can go one layer deeper. So now I'm all the way inside the inlet manifold, inside this pipe, and I can see that its diameter is 0.26 meters, and that it would have worked if that manifold had been 0.244 meters, but it had to find an available pipe, and when it found an available pipe, its inner diameter was 0.26 meters. Anybody want to ask a question? You see how I drilled down into a map to get more information? So you can hunt in that. Otherwise, it's hard to see inside these maps. So I created that tool to make it a little bit easier. Okay, then with no questions, I'm ready to switch to Gather. See you in Gather. And there's two questions that are in the chat, which I'd like you to talk about with your team first. And maybe Claire and I will divide up and come around to different ones of you and see what you can come up with for those questions, and also be ready to answer questions about the design challenge. See you in Gather. Bye.